Good morning. I am a PhD student from the University of Parma. In our research, we have studied the fractal toughness of highly deformable polymeric materials. A brief summary. I start with an introduction on highly deformable polymers, so the performance test and the interpretation of the results. As we know, highly deformable materials have a high fractal toughness due to their great deformability. In this research, we present the results of some experimental tests performed on fluid specimens made of a common silicon-based polymer. This material was is adopted in several industrial applications, like biomedical, but it was chosen because it represents a class of material. The material was, before the other test, was characterized by a simple traction test that showed the elastic behavior, which is nearly hyperelastic up to failure, with an increasing of the stiffness with the increasing of strain. The material is isotropic, and the effect of plasticity or internal damage is negligible. The failure is brittle. As we know, the crystalline material has an enthalpic elasticity, so the elasticity is ruled by the internal energy of the crystal. For a polymer, the polymer is made of a network of long molecular chains linked together in a network, and the mechanical behavior is ruled by the entropy. In this general equation, the internal potential energy is related to the entropy variation and the temperature. So, always the polymer network is in a state of thermodynamic equilibrium. For example, this one is the constitutive equation derived from this one for a neo-Buchanan medium. Polymers have a high fractal toughness due to the high deformability, because the chains are rolled together, and they are rolling. The elasticity is due to the unrolling of the chains and with a subsequent alignment on traction direction. This process takes time, and so the fractal toughness depends on the strain rate, because this process is a time-dependent phenomenon. Failure of the polymer can be interpreted with the so-called quantification criterion. With following this criterion, we assume the presence of intrinsic microspherical voids embedded into the material, and the voids are subjected to an internal pressure equal to the hydrostatic stress into the same point of the material. The failure occurs when a critical value of this pressure is attained. When this criterion is fulfilled, we have an unstable inflation of the void, causing a brittle failure. The criterion can be wrote in this way, where it depends only to the fractal energy, the average size of the void, and the hydrostatic pressure. When the void is expanding, the stress stays in the region vanishes completely. The experimental test we have performed on these non-standard specimens. The specimens were pre-created thin plate made of this silicon polymer. We tested 4 different crux lengths and 3 different strain rates. This one is the complex table of the test. During the test, we have observed in the thin plate the out-of-plane displacement of the regions above the crack, as Professor Bolzoni showed yesterday. This phenomenon is due to the instability closure of the transversally compressed zones. And we can observe also the blunting of the original crack tip, and the blunting become more evident, decreasing the strain rate. Also, for new crack tips, or direction of the tip appear during the load process. The observed failure mechanism is breakable. This one are several Green-Lagrange strain maps obtained from digital image correlation for the 20 mm and the 50 mm crack two strain rate. We can observe the gradual magnification of the stress in a region, not only in the near of the crack tip, but in the region. And this one are the crack paths highlighted after the complete rupture of the specimens. We can see that for an increasing strain rate, the crack path has is not perfectly straight, but has an initial curve. So in this case we are in a mixed mode, and in this case a pure mode 1. Here we have two videos only for showing the advance of the test. You see the blunting of the tip and the 4 new tips. And in this case, which is the slowest, you see the same phenomena. I'm sorry for the motion of the camera. I'm not a great camera operator. At the end of you see the great deformation. This one is the fastest test, and this one the slowest. We can see that for the failure start from this point. The fracture energy of the specimen can be calculated from this simple expression, in which at the numerator we have the total energy spent for the rupture, and at the denominator the total flex area. This term can be calculated from this simple expression, in which compare only the stress intensity factor in mode 1. Introducing in the expression, in this the stress intensity factor expression in this formulation, to obtain the last equation, in which compare this function we have introduced. It takes into account the reduction of the remote stress during the fracture propagation, and it is estimated using several finite element analysis. We can see the results of the calculation. In these two cases, we see for all the tested specimens, the fracture energy calculated assuming that these two hypotheses. In the first, we assume the recovered elastic energy was equal to 0. And in this case, it was calculated with using the previous expression. We can see that the difference between the two cases is about 1 order of magnitude. So the elastic energy recovered is not negligible. Also, we can see that for the high strain rate, the fracture energy is lower. Using the cavitation criterion we have shown before, we can compute the average size of the intrinsic internal micro effect using this equation. And we have obtained these results, which are quite dispersed, but we can observe that there are the mean value is about 0.1, 0.2, really 0.4 millimeters for the specific material we have chosen. In conclusion, we have observed that polymer exhibit high defect tolerance, and fracture energy appears to be sensitive to the strain rate, in particular material shows a lower fractal energy for high crystalline rate, and the fluid elastic behavior has been observed in the material up to the final brittle failure. We have provided also an estimation of the size of the micro defect using the cavitation criterion, which is a common criterion